Student's t-distribution. A t-distribution looks exactly identical to a normal distribution in that both distributions are bell-shaped. However, the difference is how wide the t-distribution is stretched out. This in turn depends on what's called the degrees of freedom, which is simply equal to the sample size minus 1. Now in particular, the larger the sample size, and therefore the larger the degrees of freedom, the more accurately the sample would reflect the population average, and thus there will be less deviations around the sample mean. In other words, the t-distribution will be tighter. So that's a lot of information. Let's have a look at each important point. First of all, when it comes to t-distribution, the sample size matters. But we don't exactly look at the sample size. We look at what's called the degrees of freedom, which is simply sample size minus 1. So depending on the degrees of freedom or sample size, it'll affect the distribution of all the possible values. Now here's what we're saying. The larger the sample size, and therefore the larger the degrees of freedom, the more accurate the sample would be. Now, doesn't that make sense? I mean, even without doing any quantitative analysis, doesn't it make sense that the larger the sample, then the more accurately it will reflect the parameters of the underlying population? So I would much rather rely on data from a large sample than data from just, let's say, 5 observations. So that's the logic here. So if you do have a larger sample size, there will be less deviations around the sample mean, meaning that we would be more confident in the sample mean, and therefore there'd be less uncertainty around our estimate for sample mean. So there you go, ladies and gentlemen. You cannot do quants without knowing the underlying story behind it. Otherwise, you're just memorizing things, right? So to illustrate, suppose that we want to construct a 95% confidence interval around our estimate for population mean. So let's stop right there. What's going on here? Well, the thing with population mean is that it is unobservable. I mean, that's the whole point of doing statistical analysis, is that we can't observe all the values, and that's what population is. So what we're going to do here is from our sample, we're going to make some inferences about the population mean. But because we're using a sample, there's going to be some uncertainty. And what we want to do, therefore, is we want to construct a 95% range around our estimate. So what we're saying here is we want a 95% range within which there's a likelihood that the population mean falls within. Now, if we are using a normal, or also referred to as a z-distribution, then the range around our estimate would be plus or minus 1.96. And we've seen this from a previous module. So if you're looking at a 95% range around the mean, and you're assuming that the variable is normally distributed, you'd have to go plus or minus 1.96 standard deviations on either side of the mean. And this is what it would look like. So a 95% confidence interval, here's our sample mean. We would deviate plus or minus 1.96 standard deviations on either side. However, if we are using t-distribution, that same 95% range would be dependent upon sample size. So that is the main distinction with t-distribution, is that its distribution is dependent on sample size. So let's look at some sample sizes. In the first case, let's see, we have a sample size of 10, so that works out to degrees of freedom of 9. So if you wanted to construct a 95% confidence interval using t-distribution, so here it is, let's match up everything. So here it is, 9 degrees of freedom, 95% confidence interval, and if it's a t-distribution, the t-distribution says you would have to deviate plus or minus 2.262 standard errors away from the mean. And now I want to show you where I got that number from. But before we go to the table, there's just one thing I want to point out, If the body is 95%, that would mean there's 0.025 for either tail. And that's the information we need in order to calculate the standardized value. So again, a 95% confidence interval coincides with each tail being 0.025. So this is our student's t-distribution, and notice that we just need to indicate what the probability is for each tail. Now remember, we said that the tail area, if you're doing a 95% confidence interval, each tail would have an area or a probability of 2.5%, but of course we express it in decimal format, so it's 0.025. And the other thing we have to express is degrees of freedom. So we're looking at 9 degrees of freedom. So when you triangulate, you get a standard deviation, or I should say a standardized value of 2.262. And that's where these numbers came in from, right? So I just want to make sure we're following up until now, ladies and gentlemen. So very quickly, we just want to construct a 95% range around our estimate for population mean. So here's the possible scenarios. If we assume normal distribution, then it's a done deal. We just need to go plus or minus 1.96. But if we assume that the variable is exhibiting a t-distribution rather than normal distribution, the only twist is we have to indicate what the degrees of freedom is. So if the degree of freedom is 9, and assuming it's exhibiting a t-distribution, rather than the range being plus or minus 1.96 standard deviations away, for that same 95% confidence interval, now you would need to deviate plus or minus 2.262 standard deviations away from the mean. So what would happen now if the sample size was 50 and therefore the degrees of freedom was 49? Let's go and have a look at our table. Here we are. So basically this table is really just cut in half, so it just continues. So it starts from here and then it just continues. Now the one we're interested in is 49, so there's 49 degrees of freedom. And again, the 95% confidence interval corresponds with a tail area of 0.025. So once again, when we triangulate, we get a value or a critical value of 2.01. And that's exactly where we got this number from. So notice for that same 95% confidence interval, as the sample size increases and therefore the degrees of freedom gets higher, now what starts happening is that the confidence interval narrows. And actually that's a good thing, because now it's saying that the uncertainty around the sample mean is getting smaller and smaller because the sample size is getting larger and larger. Now the final scenario is if the sample size is infinity. So obviously we're looking at theoretical scenarios here. Therefore of course infinity minus 1 is also infinity. So if you go back to our table and you look at degrees of freedom of infinity, and they do have one here, so infinity, and again I'm looking under the column that has a tail area of 0.025, you get 1.96. And there it is. And what's interesting is that this 1.96 critical value is the exact same critical value that you would have got had we assumed normal distribution. So what's the logic here? Notice how as the sample size and therefore degrees of freedom increases, the t-distribution converges into normal distribution. In other words, the critical value becomes 1.96. And again, the logic is that with such a large sample size, the deviations or the errors around the sample mean would be normal. On the other hand, for smaller sample sizes, the t-distribution widens, accounting for the fact that there might be more dispersion, i.e. errors around the sample average. Now we touched on this, but let's just look at it again. Look at the difference. Look at the difference. And this is really important from a logical point of view. In all the cases, we're constructing a 95% range around the sample mean. But when your sample size is small, we need wider goalposts because there's a lot more error. But when the sample size is large, then we can afford narrower goalposts, indicating that there's less errors around our estimate because the sample is getting larger. Now, the other observation is that as the sample size keeps getting larger, the t-distribution converges to a normal distribution, because you can see that in both cases the critical value is 1.96. So we've got 1.96 here, right? And that's associated with normal. And you got 1.96 here, which is associated with t. So as I said before, think of t-distribution as winding the goalpost to account for greater errors associated with smaller samples. And that's really how it's done in practice, ladies and gentlemen. So when you have a small sample, or you don't have too much confidence in your sample, in other words, the sample is unreliable, most analysts use t-distribution so that they can factor in wider goalposts. As a result, a t-distribution is regarded as the more conservative approach to testing, as it accounts for more errors around the estimate. And like I said, so if you're not confident in the data, if you think the sample is unreliable, it's better to use an approach that relies on wider goalposts, and that means using t-distribution.